Welcome students. Okay, welcome to our material science lectures. Now, we have seen how solids are divided into two types, amorphous solids and crystalline solids. Okay. Now, crystalline solids have a regular structure we have seen. Okay, studying that structure of crystals comes under what is known as crystallography. Okay, crystallography means studying the structures of crystals. Okay, right? Now, what is a crystal means? A crystal is one where the atoms or ions or molecules are arranged in a very systematic manner. That's what we have seen. Okay, now I'll divide in order to understand the crystal structure or analyze the crystal structure. What I do is, I will divide the crystal into two types. Okay, right? Two parts, right? One is lattice, other one is basis. Okay, lattice and basis. What is a lattice? Okay, basis or motif also we call it. Now, what is lattice means? Suppose say this is copper crystal in which copper atoms are like this. In order to understand the structure of this copper, what do? I'll remove all the copper atoms, and wherever one copper atom is there, I'll put one imaginary point there. Okay, like this. Okay, I'll put one imaginary point. Okay, for this atom, in some place, I'll put one point here. For this atom, I'll remove that atom and put one point there. And for this atom, I'll put one point here like this. Every atom is replaced by a simple geometric point. Okay, the collection of the simple geometric points is known as lattice. Means lattice does not contain any atoms. Okay, it is not even the actual crystal. In nature, actual lattice does not exist. It is an empty skeletal structure. That's all. Now, these points are called lattice points. What do they indicate? Okay, this roughly gives me the structure in which the atoms are arranged here. At each lattice point, okay, I have to put either one atom or two atoms or ions or molecule, whatever it is. Okay, right? This is known as lattice. Okay, this is lattice of copper, I'll say. Now, what is the difference between crystal and lattice? In crystal, we have the actual atoms present. It physically exists, whereas lattice does not exist physically. It is in my imagination. Okay, it contains only points known as lattice points. We call that so. Okay, now how to get the actual crystal means at each lattice point, right? Keep that atom or ions or what you call group of atoms, molecules, whatever it is. Okay. Now, if I say this is a crystal lattice of copper means, okay, at each lattice point I have to put one copper atom. At each lattice point I have to put one copper atom here. When I put what you call replace each lattice point with the copper atom corresponding, I'll get the actual crystal, copper crystal I will get. The actual copper crystal I'll be getting like this. Okay, so at each lattice point I'm putting one copper atom. That is, the atom or atoms or ions, whatever it is, right, which I have to put at each lattice point in order to get the actual crystal, that is known as basis. Okay, basis. So, basis of copper crystal contains what? Okay, contains, right, one basis contains one copper atom. Means, at each lattice point, I am putting one copper atom such that I will get the actual copper crystal. Okay, means what happened? Lattice plus basis gives me the actual crystal structure. Okay, lattice plus basis gives me the actual crystal. Okay, that basis may contain one atom. In the case of copper, it is containing one atom. Okay, in the case of ice, it may contain one H2O molecule. Okay, in the case of NaCl, it may contain one Na plus and Cl minus ion, like that. Whatever atoms or atoms or ions or molecules, whatever you have to replace, at each lattice point, in order to get the actual crystal is known as basis or motif we call. So, lattice plus basis will give you the actual crystal structure. Sir, you may ask me why you are dividing like this, sir. Directly we can study crystal only now. Means it becomes easy because different crystals may have same lattice structure. Okay, right? Same crystal may have different lattice structures also. Okay, like this. Now, example, zinc sulfide is there. Okay, zinc sulfide can crystallize in cubic form or in hexagonal form also. Okay, crystal is same, zinc sulfide only, but the structure inside, lattice structure is different. Similarly, copper, silver, gold, these three are known as noble metals. They all crystallize in FCC structure. Okay, so if I study the lattice structure of copper, it is sufficient, right? I don't have to study silver and gold structures. Why? Instead of copper atoms, if you put what you call silver atoms, you will get silver crystal. Replace silver with gold, you will get gold. Okay, means if you simply study the lattice structure of this what you call noble metal sufficient, you don't have to study all the three metals separately and independently. Not required. Okay, one lattice is sufficient because At that lattice, you remove copper atoms and put silver. Basis is different. That's all. Means copper, silver, gold all have same lattice, but their bases are different. Okay. Copper basis contains copper atoms. Silver crystal contains silver basis is silver atoms. Similarly, gold basis is gold atoms. That's all. Okay. Means you study the lattice, it is sufficient. Okay. You don't have to study. There are thousands of crystals available in nature. You don't have to study all thousands of crystals. If somebody says, right, A, B, C, D, E, F, G, H crystals have same lattice structure, I'll study that lattice structure sufficient. I've understood about all crystals. Okay, similarly, means what? Different crystals may have same lattice structure. Okay, same crystal may have different lattices also. Just like I have given the example of zinc sulfide. Okay, so it's advantageous and convenient for us to divide the crystal into lattice and basis. So lattice plus basis gives you the actual crystal we say. Now, a crystal contains how many? I told you, a small cubic centimeter of a crystal also contains approximately 10 to the power 22, 10 to the power 23 atoms will be there. Okay, in order to understand the crystal structure, I don't have to go to all 10 to the power 22 atoms. One lifetime is not sufficient. Okay, impossible for us to cover all atoms. So what do? Imagine, I'll bring the concept of what is known as a unit cell. Okay, and now I'll imagine a crystal is equal to a big college building where there are 100 rooms. Okay, now suppose say UPSC wants to take that college as examination center for engineering services exam. So one team of officials will come to inspect, right? How many students can be accommodated in that examination center, how many insulators are required, how many supporting staff are required, etc. etc. Or whether ventilation is sufficient or not, etc. etc. They want to come and study. So they will go to one room, measure its length, breadth and height, okay, see how many benches are there, how many students can be accommodated, in so and so a safety area, so many students should be accommodated. There will be some calculations will be there for them. How many tube lights are there, how many fans are there, whether ventilation is good or not, how many insulators are required, how many supporting staff are required, etc. etc. They calculate for one room. When they are going into the second room, the college principal comes and says, sir, we have 101 rooms here, all 101 rooms are identical. So what does that mean? Right, the team need not visit all 101 rooms. Okay, one room if they study it is sufficient. All that they have to do is what? Into 101. Okay, that one classroom is the representative unit of the entire college building. Okay, because the remaining college is nothing but a repetition of this room. That's all. Okay, there is one room here. Put another room, another room, another room, another room on the top, another room on the top, another room at the back, and one room in the front, one room to the left, one room to the right, like that. You expand that one room, you repeat that one room in 3 dimensions, you will get the complete college building. Okay, similarly, in a crystal also, because there are 10 to the power 22 atoms or 10 to the power 23 atoms, it is impossible for us to go and go to each and every atom and see. So I look for the smallest representative unit in the crystal, in the lattice, whose regular repetition develops the actual crystal. Means, suppose a lattice is like this. A lattice is like this. Lattice points are like this. Okay, right? I'm only trying to understand the structure. That's all. Okay, I'm not interested in the actual crystal. I'm interested in the structures of the crystal. Okay, suppose say a lattice is like this. These are all lattice points. Okay. Now I look for the smallest representative unit whose regular repetition along the 3 dimensions gives me the complete crystal. Means, suppose I'll take like this, something like this. Okay. This is my smallest representative unit. Remaining crystal is nothing but a repetition of this crystal, of this smallest unit cell only. Means this part is nothing but, you repeat the structure here, you repeat the structure here, again you'll get this one. You repeat the structure here, again you will get like this. You repeat the structure here, again you will get like this. Means what? You study this part of the lattice, it is sufficient. You understand the properties of, or the structure of this part of the lattice sufficient. Remaining lattice is nothing but a representation of, or repetition of the entire lattice. Okay, the smallest representative unit whose regular repetition along the 3 dimensions gives the complete crystal is known as unit cell. Okay, so unit cell is like one single room in a big college building containing 100 or 120 rooms. Okay, you study that one room, you are understanding the entire college. Similar like a hotel room. Hotel contains 60 rooms are there. All rooms are identical only. You go and check one room sufficient. Remaining room 59 rooms will be similar. Okay, same is the case with unit cell also. Now, a typical unit cell is a three-dimensional one space. In three-dimensional space, a typical unit cell can be drawn like this. I'll draw a typical unit cell like this. Okay, I'll draw a typical unit cell to be somewhat like this. Very roughly and vaguely I'm drawing. Okay. I'm drawing something like this, a vague figure I'm drawing. Okay. It is three-dimensional in space. Okay. Along one direction, I'll call this as x-axis. Another one, I'll call it as y-axis. Okay. Another one, I'll call it as z-axis. These x, y, z are called crystallographic axis. Crystallographic axis. Okay, they are not coordinate axis, remember. They are not coordinate axis. Coordinate axis means x, y, z will be mutually perpendicular. Okay, here, angle between x and y and z and x may be 90, may not be 90 depending on this. That's why I'll call them as three different directions are required for three-dimensional entity. So I'm putting three directions. They are called x, y, z are called crystallographic axis. Okay. The length of the unit cell along x-axis, I'll call it as a bar. Okay, length of the unit cell or size of the unit cell along y-axis, I'll call it as b bar. Length of the unit cell along z-axis, I'll call it as c bar. Okay, this a bar, b bar, and c bar are called lattice constants. Okay, the angle between what you call x and y is known as the angle between x and y. I'll take it as gamma. Okay, the angle between y and z, I'll take it as alpha, and the angle between x and z, I'll take it as beta. Okay, these alpha, beta, gamma. Okay, alpha, beta, gamma are called interfacial angles. Okay, interfacial angles. Alpha, beta, gamma are called interfacial angles. ABCs are called lattice constants. Okay, these lattice constants ABC and interfacial angles alpha, beta, gamma put together, they are known as lattice parameters. Okay, this is a typical room. Okay, just like a typical room. Okay, a room may be rectangular or a room may be cubic or room may be semicircular. Some rooms may be triangular, some L-shaped rooms will be there, like the different types. So how many different means? And in general, one unit cell is drawn like this. Okay, right? These are known as 6 parameters are there, lattice parameters I'll call. Okay, now we have to put lattice points in them. Okay, in this unit cells, right? A scientist called Bravais. Sorry. Okay, scientist called Bravais. S is silent there. Okay, Bravais has proved that in space, in three-dimensional space around us, atoms can be arranged in only 14 different ways. That's all he said. It is very surprising. Atoms are 10 to the power 20, billions and billions and billions of atoms will be there. But in how many ways they can be arranged? Crystals are also, lakhs of crystals are there. But in lakhs of crystals, right, billions of atoms, right, how many ways atoms can be arranged in three-dimensional space? Means Bravais has proved that there are only 14 types. Okay, 14 different types of arrangements only are possible in three-dimensional nature. Okay, they are called Bravais lattices. We call. Okay, only 14 types of lattices are there. So number of Bravais lattices in nature are how many? 14 types of Bravais lattices. In order to accommodate these 14 types of Bravais lattices, how many types of what you call unit cells are sufficient? Means what has been observed is to accommodate all the 14 types of atomic arrangements or Bravais lattices, only 7 types of unit cells are sufficient. Okay, 7 types of unit cells means room configurations are sufficient. It has been observed. Means 7 unit cells they are called 7 crystal systems. 7 crystal systems are sufficient to accommodate all the 14 types of Bravais lattices. Means it is like this arrangement, atomic arrangement means what? In a room, suppose a crystal is like a room, okay, in which the benches should be arranged. Where do you arrange benches? Benches are usually arranged only on the floor. You go to any country, anywhere, any classroom, not only now or 100 years back also. Okay, right? Benches are always arranged on the floor only, no. Never we can expect vertically. You might not have seen a classroom where the benches are hanging to the ceiling, isn't it? Or two benches are fixed to the wall like a flower vase or like a painting. Okay, asking two students to go and sit there. It is impossible. Okay, it's not a stable configuration. Okay, stable configuration means in anywhere you go to Oxford or MIT or IIT or wherever it is. Okay, right? The benches are always on the floor. Only thing is some maybe two-seater benches, three-seater benches, four-seater benches, or individual chairs. Okay, those chairs or benches may be arranged in normal one after the other form or semicircular form that way, but nobody will hang what you call chairs or benches to the ceiling and say it is one different type of arrangement. Okay, similarly, atoms in three-dimensional space also can be arranged only in 14 different ways. Okay, they are called Bravais lattices. Okay. Now, what are the what's called the 7 types of crystal systems? Means 7 types of unit cells, and right, which type of Bravais lattices are possible in each type of unit cell? Means how these 14 types of Bravais lattices will fit into these 7 crystal systems. Now we'll see. Okay, right? I'll give you one chart. Right, this chart is very important from exam point of view. You have to by heart this chart because every year one gunshot question will come. One question is gunshot. Okay, it will come. That's all in the examination. In one exam or the other, you will find a question in what you call from the chat which I am going to give. Okay, there is no other go. You have to by heart. Of course, there is a simple way of recollecting the entire chat. Okay, or remembering the entire chat. That also I'll tell you. Okay, right now before going into that, we'll give you one more nomenclature. Okay, the lattice type. I use the word P. Okay, P means primitive. Okay, P means primitive. Okay, I means body centric. I means body centric. Okay, right? F means face centric. F means face centric. C means base centric. Okay, these are the abbreviations. Base centric. Okay, base centric. Base centric. Okay, right? Means suppose if I say cubic P. Okay, cubic P means it is primitive or simple also. There is another word, simple. Okay, right? Cubic P means it is simple cubic or tetragonal I. If I say it is body centered tetragonal, like that we have to use. This is the abbreviations which we will be using. Okay, P means simple or primitive, I means body centric, F means face centric, C means base centric. Okay, right? Now, what is the chart? The chart is given like this. Okay, right? Take your own time, slowly try to what you call get that chart into your mind. Okay, right? Very important from exam point of view. Right? First one, the first column in the chart will be crystal system. Okay, crystal system. Next one, lattice parameters. Lattice parameters. Okay, next one is okay. Next one is known as possible Bravais lattice types. Possible Bravais lattices in that crystal system. Okay, right? Next one, their number. Means how many types of lattices. Whatever we write here, we'll put that number here. And next one, number of independent parameters. Number of independent parameters. What are these? We'll see now. Okay, right? So the first column is crystal system. Second one is lattice parameters. Okay, the third one is possible Bravais lattices, their number and the number of independent parameters. Okay, the first crystal system is cubic system. First one is cubic. Here A is equal to B is equal to C, alpha equal to beta equal to gamma equal to 90 degrees. Okay, means all three sides are equal. All three angles are also 90, 90, 90. Okay, that is nothing but the simplest of all crystal systems. That is nothing but cubic system. How many types of Bravais lattices are possible? P, I and F. P, I and F. Okay. We are using the abbreviations now here. Cubic P means it is simple cubic. Cubic I means body centered cubic or BCC. Cubic F means face centered cubic structure or FCC we call. Okay. So to simplify, we are using this abbreviation. Their number, how many Bravais lattices are possible? PIF, 3 types. So I'll put 3 here. What are independent parameters? I'll come to it later on. Okay, the second one is what is known as tetragonal. Okay, tetragonal. Here, A is equal to B, not equal to C, but alpha equal to beta equal to gamma equal to 90 degrees. All three are 90, 90, 90. Okay. Here, 2 types of Bravais lattices only are possible. Simple and I, P. P means what? Tetragonal. P means simple tetragonal. Tetragonal I means, right, it is body-centric tetragonal. Okay, so 2 types of Bravais lattices are possible. I'll write 2 here. Their number is 2. Okay, third one is what is known as orthorhombic. Third one is what is known as orthorhombic. Orthorhombic. Here A not equal to B not equal to C, but alpha equal to beta equal to gamma equal to 90 degrees. Okay, here all 4 P, I, right, F and C. Okay, means simple, body centric, face centric and base centric orthorhombic systems. All 4 are possible here. So I'll put 4 here. Okay, 4 Bravais lattices are possible. Okay, the next one is trigonal. Okay, trigonal, or sometimes it is known as rhombohedral also. Rhombohedral also you can call. Okay, trigonal. Here A equal to B equal to C, but alpha equal to beta equal to gamma not equal to 90 degrees. Means all 3 sides are equal, but none of them is equal to 90 degrees. Okay, right? Here only one type is possible, simple. Okay, so I'll put only 1 here. Okay, simple or trigonal is possible. Sometimes some books will find it as R also. That is rhombohedral structure or trigonal Bravais lattice. Okay, the next one is hexagonal. The 5th one is hexagonal. Hexagonal. Here A equal to B not equal to C. Okay, alpha equal to beta equal to 90 degrees, gamma equal to 120 degrees for hexagonal system. Here also, okay, only one type of lattice is possible, simple, that is one I put here. Okay, right, that is hexagonal system. So next 6th one is what is known as monoclinic. Monoclinic. Here A not equal to B not equal to C, alpha equal to beta equal to 90 degrees, not equal to gamma. Not equal to gamma. Okay. Here 2 types of possible, simple and base centric. So I'll put number of Bravais lattices as 2. Okay, the last one, 7th one is triclinic. Okay, triclinic. Here, right, A not equal to B not equal to C, alpha not equal to beta not equal to gamma not equal to 90 degrees. Okay, here also only simple is possible, that is one type of Bravais lattice only is possible. Okay, so these are the 7 types of crystal systems possible in nature and the possible Bravais lattices in them and their number. How many are there? 3 plus 2, 5 plus 4, 9, 10, 11, 13, 14. 14 types of Bravais lattices are there completely. Okay, 14 types of Bravais lattices are possible in nature and the possible crystal systems like this. Okay, this is the complete chart which you have to by heart, no other option. Okay, right, you have to by heart this chart, remember this chart. Okay, because one question definitely is appearing in every exam from this chart. Okay, crystal structure. So it is like this, how questions can come. Okay, the lattice parameters of trigonal system are, okay, they will give you 4 options. You have to choose A equal to B equal to C, alpha equal to beta equal to gamma but not equal to 90 degrees. Okay, or another question, for which type of crystal system the lattice parameters are A equal to B not equal to C, alpha beta are 90 but not equal to gamma equal to 120 degrees. Means you have to identify that it is hexagonal system like that. Okay, means they may give you lattice parameters and ask the name of the crystal system, or they may ask the crystal system and ask for its they may give the crystal system and they may ask for its lattice parameters. Or another type of questions may also come. Okay, in which type of crystal system all three angles are orthogonal but only two sides are equal. Okay, all three angles are orthogonal, all three are orthogonal means what? Alpha, beta, gamma, all three are 90 but only two sides are equal, means A equal to B not equal to C, means you have to identify it as tetragonal like that. Okay, or one more type of question is, in orthorhombic system, how many types of Bravais lattices are possible? 1, 2, 3, 4. Like that they will give you. Okay, 4 types of Bravais lattices are possible. In hexagonal, how many types of Bravais lattices are possible? Okay, 1, 2, 3, 4. They will give you option. In hexagonal, only one type of Bravais lattice is possible like this. Okay, so these are the what you call the 7 crystal systems. Okay, when you go through any crystal, okay, it will be in one of these 7 crystal systems only. Okay, it will belong to these 14 types of Bravais lattices only. Okay, so next one, number of independent parameters. This one column we have to fill now. Okay, how do I start? Now, suppose I'll ask you to draw a cubic unit cell in your notebooks now. Okay, so I'll ask you to draw a cubic unit cell in your notebooks now and show me. I'll say, okay, what do? You will ask me one question. What is that? When I ask you to draw a cubic unit cell in your notebooks, you will ask me one question. What is that? Sir, why should we draw, sir? You want to draw, you draw yourself. Is that the question you put? No. What question do you ask me? You'll ask me, sir, what is the side? Okay, if I say a cube of side 3 centimeters means immediately you will take one scale, you will draw one line 3 centimeters. That is sufficient because you know that all 3 angles are 90, 90, 90. All 3 sides are equal. So you will draw a cube of side 3 centimeters like this immediately. Putting all 3 angles as 90, 90, 90, you will immediately draw a cube with side equal to 3 centimeters. With side equal to 3 centimeters means how many parameters are required for you to draw a cube? Only one parameter, one side is sufficient. Means the number of independent parameters required to describe a cubic unit cell is only one, that's all. Okay, you specify its side, remaining things you can draw. Okay, similarly, if I ask you to draw tetragonal, okay, tetragonal unit cell in your notebook and show me, means what do you do? You know tetragonal, all 3 sides are 90 only, but only 2 sides are equal. A equal to B, not equal to C. So, now you will ask me how many questions? You will put 2 questions to me. Sir, what is A, what is C? Because B is equal to A only now. So, if you know A and C is sufficient, alpha, beta, gamma are anyway 90 degrees, isn't it? Okay. So, here you require 2 parameters to be given. Okay, unless suppose you are writing a C program. Okay, you input that means you input the data. The program should be written is written in such a way so that it displays the unit cell on the screen. Okay, so you will write one program. If you are writing a program for cubic unit cell, right? You will ask, take alpha as beta equal to gamma equal to 90 degrees, right? A equal to B equal to C. Ask for A. So the moment somebody has to draw one unit cell, show me one cubic unit cell. The question comes: what side you want? So if you put 4 centimeters, 4 centimeters cube will be displayed. If you put 6 centimeters, 6 centimeters cube will be displayed. Similarly, if I want what you call tetragonal unit cell to be displayed, the number of in the program you have to extend it. Okay, right? Ask for A. Then A input should be given 3 centimeters. Ask for C equal to 2 centimeters. Then immediately the computer screen will display me a tetragonal unit cell. Means the number of independent parameters required to describe a tetragonal system is how many? 2. Like this. Okay. What about orthorhombic? Okay. Orthorhombic also, alpha, beta, gamma are 90 only, no? They are known to us. Okay. So, but A not equal to B not equal to C means you should specify, right, A, B, C separately. Means how many parameters are required here? 3 parameters are required to draw one orthorhombic unit cell in our notebook. Okay. Next, trigonal. Just guess. How many are required for trigonal? Alpha, beta, gamma, all are equal but not equal to 90. So, but A equal to B equal to C. Means if you know any one side it is sufficient. All 3 sides are equal, no. So, this is one parameter you require. And alpha, beta, gamma, all 3 are equal but not equal to 90. How much that angle should be? Whether 80 or 90 or 100, whether 80 or 100 or 120 or 60, I should specify. Okay, means this one angle should be given, one side should be given, means number of independent parameters required will become hexagonal. Tell me just hexagonal, how many parameters are required? You yourself can guess. Okay, right? How many parameters are required? See, alpha, beta are 90. That is fixed. You cannot say hexagonal means alpha and beta will be 90. Gamma will be 120 only. That you and I cannot change. Okay, the structure itself is like that. Okay, A equal to B, not equal to C. A equal to B, not equal to C means what? If you know either A or B sufficient and one C should required, means what? One here and one this one. Alpha, beta and gamma are fixed only now, isn't it? So only two parameters are sufficient to describe a hexagonal crystal unit cell. Okay, monoclinic, again you guess, monoclinic, alpha and beta are 90, you and I cannot change it. Okay, but not equal to gamma. Gamma should be given. How much should be that gamma, whether 85 or 95 or 109, something like that. Okay, so one gamma is required here. And A not equal to B not equal to C means what? Okay, all three should be known to us. All three sides should be known and one angle should be known. Means again, four parameters are required to describe a monoclinic system. What about triclinic? Okay, triclinic, none of the sides are equal, none of the angles are equal. Means all six parameters should be specified. Unless I say A equal to 4 centimeters, B equal to this much, C equal to this much, take alpha this much, beta this much, gamma this much, you cannot draw a triclinic unit cell. Okay, so number of parameters required to describe a triclinic unit cell is 6. That number is equal to 6. Okay, see 1, 2, 3, 2, 2, 4 and 6. Okay, now which system is simplest of all? Which system is the most difficult one? Okay, right? Now if I ask you which system is simplest one, means you will immediately say, sir, cubic system is simplest. Why? All three sides are equal, all three angles are also 90, 90, 90. Easy to draw also, isn't it? Okay, but which is the most complicated system? Which is the most complicated system means, in the classroom, some students will say, sir, monoclinic is most complicated, or trigonal is most complicated, or hexagonal, or triclinic, they say. Okay, most complicated means not difficult to us. Okay, right? Triclinic in that way. See, in cubic, all three sides are equal, all angles are same. In triclinic, none of the sides are equal, none of the angles are also equal. That way also you can remember, no? So it is easy to remember triclinic, but difficult to draw triclinic. Why? Unless you specify 6 parameters, I cannot draw a triclinic unit cell. 6 parameters are required. Means if you are writing a computer program, right, you have to input what you call, you have to write the program in such a way so that it asks me 6 questions. So ask for A, ask for B, ask for C, ask for alpha, like that. 6 questions should come one after the other. Then only when I give all the 6 parameters as input, right, a triclinic unit cell will be displayed on the screen. So triclinic is the most complicated system. Cubic system is the most simple system. Okay, so this chart is very, very important. Again, I am stressing on this point. Okay, make it a point to by heart this chart. And which way to remember, sir? What is the easiest way? The way I have drawn itself is the easiest way to remember. Okay, in textbooks you won't find in this order. In textbooks you won't find in this order. I have written it in such a way such that here, see, all are equal, all angles are equal. Okay, here also all angles are equal, but only one side is not equal. Okay, here all three sides are not equal. Means one not equal to, two not equal to, all are angles same. Again, when all are not same, then again all are same, but all angles are equal but not same. Okay, like this I have drawn in a systematic manner. I have arranged all these 7 terms. Okay, this is the way you have to remember. It may take 1 or 2 days time to remember, but slowly keep on going it through. Every day at least once. Okay, for 5 minutes or 10 minutes, just practice this. Okay, it will not a very difficult thing or impossible thing. It needs a little bit of attention from your side. Nothing wrong, because you are going to get 1-2 marks for sure. Okay, one question is going to come anyway from this topic. You are going to score 1 mark also. 1 question or 2 marks. Okay, right? Now, about which system we will be studying now? Okay, just tell me. We will be studying mostly cubic system. Okay, sometimes you study hexagonal system also. Why means? Because they are simplest. Nobody wants to study complicated system like triclinic. In no textbook you will find triclinic system also. Why? Because okay, is it because it's very complicated? No. Okay, cubic is sufficient for us to understand 90% of things around us. Okay, cubic system is sufficient, and some are hexagonal. That's all. So we concentrate mostly on cubic and hexagonal. So in our next video, we will go into what you call the cubic system. Okay, and what are the three Bravais lattices? What do they mean, right? Where do we put atoms in a cubic unit cell? That will be discussed in the next chapter, okay, next video, right? Thank you for today.